Take a moment to read Unit 4, Problem 17.2, How long will it take? In this activity, students begin to learn about logarithmic functions in a real-world problem about population growth. Students have previously looked at population growth with exponential functions. Now we're asking students to represent them as a function of population size. There are a few strategies students can use in this problem. They could evaluate logarithms using a calculator, or rewrite logarithms as an exponent to find the missing value. In the first part of this problem, it's asking us to explain why log base 2 of x to represent the number of hours h, it takes 1,000 bacteria to reach a population of x thousand. So why are we writing it as a logarithm? Well, let's first think of it as an exponent. If we wrote it as an exponent, we could write it as 2 to the h power equals x. This would be where x is the number of bacteria after h hours. In this, we're trying to find x, and h is our input. With a logarithm, we're trying to find h. And we need x to be our input. So we could write a logarithm, or an equivalent equation, log base 2 of x equals h. So our input is now x, and our output is now h, hours. So using this idea, let's complete our table. They're giving us our input of x, and we need to find our output of h. There's two ways to go about this. We could evaluate using a calculator. So in a Desmos calculator, I could click the keyboard, go to functions, then go to calculus, and find the button that says log base a, and type in the function log base 2, and then plug in my input of 1. So log base 2 of 1 in the calculator is 0. And then do this for each of our logarithms. So log base 2 of 2 is 1. Log base 2 of 4, 2. Log base 2 of 8 is 3. Log base 2 of 16 is 4. Log base 2 of 50 is approximately 5.6. Log base 2 of 80 is approximately 6.3. We could also rewrite it as an exponent instead. So 2 to what power equals 1? 2 to the 0 power equals 1. 2 to what power equals 2? 2 to the first power is 2. 2 to what power is 4? 2 to the second power is 4. 2 to what power is 8? 2 to the third power is 8. 2 to what power is 16? 2 to the fourth power is 16. 2 to what power is 50? And this is where it gets a little bit harder. We know 2 to the fifth power is 32, and 2 to the sixth power is 64. So somewhere in between would be 50. It's about 5.6. 2 to the sixth power is 64, and 2 to the seventh power is 128. So somewhere in between, closer to 6 than 7, is going to be our answer to 2 to what power equals 80. Using our x and h values now, can we plot all of our pairs on the coordinate plane? So it looks like our spacing of our x is going to be by 2. And then our y's, our hours, is going to be by 1. So when we plot our points, our first point was at 1, 0. So 1, 0 is going to be right here. 2, 1, 4, 2, 8, 3, 4, 16, 4, 16, 50, and then 5.64. So we're just going to estimate here. Here is 5, so 5.6 is about there. And then 80, 6.32. a little bit past 6. And then if we connect our points as best we can, oops, oh, it's not a great graph, but if we connect them, we get a idea of what this shape is. So discussing kind of some observations about this graph, students may say that the asymptote here could be vertical. It looks very similar to an exponential, except it's kind of tipped sideways. So we know an exponential could look like this, and this one kind of looks more like this. So it could look similar to an exponential. Then it asks us to use the graph to kind of estimate some missing values. So if we use our graph, it says at 10 it would be right about here, which I'm going to say is about 3.3. It's a little bit past 3. 24 is here. I'm going to call that about 4.6. And then 72 is about there. I'm going to call that a little bit past 6, so maybe about 6.2.